Hola, buenas tardes. Bueno, bienvenidos y bienvenidas al primer coloquio del semestre. Mi nombre es Rodrigo Soto y voy a estar a cargo de los coloquios del Instituto de Física durante este semestre. Un par de avisos antes de comenzar con el coloquio de hoy. Los coloquios los vamos a hacer mensualmente, los días, el tercer martes de cada mes. ¿Ya? Quizá en octubre vaya a ser el cuarto martes por el receso universitario que hay en esa semana, ¿ya? Pero salvo eso, ¿no es cierto?, serían los terceros martes de cada mes, ¿ya? Ahora estamos en un webinar, ¿ya? Así que espero todos me pueden escuchar bien, ¿no es cierto?, y participar, ¿ya? Pueden hacer las preguntas, hay una parte de preguntas y respuestas en vez del chat, y ahí pueden hacer las preguntas y yo se las puedo decir directamente al charlista. ¿Okay? Entonces, eso sería. Ahora yo lo voy a introducir, ya lo voy a introducir en inglés y después él va a comenzar su charla. ¿Okay? So today we are going to have Tony Leggett as our speaker. Tony got his bachelor and PhD from Oxford University, and since 1982, he's been the MacArthur Professor of Physics at the University of Illinois, Urbana-Champaign. He has worked in several systems, superconductivity, superfluidity, dissipative system, low-dimensional systems, quantum computations, and the foundation of quantum mechanics, just to mention some. He has received several awards, such as the Maxwell Medal in 1975, the Dirac Medal 1991, the World Foundation Prize 2002, and of course, the 2003 Nobel Prize in Physics with Ginsburg and Abrikosov for pioneering contributions to the theory of superconductors and superfluids. He was also knighted by the Queen Elizabeth II for his services to physics. Okay, so without further introduction, it's an honor to have with us Sir Anthony Leggett.
Thank you. The theory which most physicists believe is the fundamental theory of the physical world is quantum mechanics. As most of you will know, quantum mechanics was discovered, if that's the right word, nearly a century ago now. And certainly it does seem to describe extremely well the behavior of matter at the level of electrons and atoms. But there's a problem. Most of us believe that the everyday world, I'll often use the term macroscopic world, the everyday world, which we experience in our ordinary life, is basically composed of electrons and atoms. So if quantum mechanics describes very well the behavior of electrons and atoms, should it not also describe all the things like chairs and cups and so forth which occur in the everyday world? But it turns out that if we really do assume that, we get some very peculiar consequences indeed. Now, for perhaps 75 years after the original formulation of quantum mechanics, this seemed to be the sort of problem that you could leave to the philosophers, because it seemed that it would be extremely difficult or impossible to get any experimental input into it. But over the last 20 years or so, that things have changed very drastically in that respect. We now can actually address, at least to an extent, the question of my title: does the everyday world really obey quantum mechanics? So that's what I'll be talking about. Next slide, please. So what's the problem? Well, let us consider a rather general kind of experiment which we could do with, for example, atoms or neutrons or electrons, let's say for definiteness, atoms. And the experiment goes something like this. We start off with atoms which start in some state A. And from state A, they can go to state E, where they're inspected directly. That's a human eye looking at the atom as it arrives. Of course, in real life, we'd have to catch them on a photographic plate or something, but essentially we can inspect them directly arriving at E. To get from A to E, they can go by either of two routes. One is through B, the upper route, and the other is the lower route through C. And we arrange that if we wish, we can actually inspect whether a given atom goes through route B or route C. So we do that by opening the little shutter at the top of the figure and just inspecting them directly, but also we can choose not to inspect. We can close the shutter. So then we don't know whether they've gone through, a particular atom has gone through B or C. So here's how the experiment runs, crudely speaking. First of all, we'll shut off path C, and we assume that in any actual example of this experiment, our experimental colleagues know how to do that. So we just block off that possibility. So we know that any atom which arrives at E has to have come through path B. And so we can measure the probability that an atom goes from A through B to E. And let's call that, by definition, P sub B. And then we can do the opposite. We shut off path B. And by doing that, we measure the probability that a given atom starts from A, goes through C to E. Call that P sub C. And finally, we're going to open both paths and measure the probability that an atom starts at A and goes, well, through either B or C to E, at least apparently so. And let's call that P sub B or C. Maybe that's a bit of a bigger question, but let's just use that as a notation. Okay, so what's the point of this experiment? Next slide, please. Yeah. So first of all, let's suppose that we actually look to see whether a given atom follows a path B or path C. And, well, not surprisingly, if we do that, we find that each individual atom does follow either path B or path C. And secondly, we find that the probability of arriving when both paths are open, P sub B or C, is simply equal to the sum of the probabilities of the individual paths, P sub B plus P sub C. And that's the common sense result. After all, if there are a number of passengers who travel from Champaign, my hometown, to Santiago on a given day, then, and suppose that they can go either through Chicago, say, or through Miami, then rather obviously the total number of passengers arriving in Santiago is simply the sum of those who came through Chicago and those who come through Miami. It's just common sense, more or less. However, suppose now that we don't look to see which path was followed. Then we find that the total probability of arrival when both paths are open is not necessarily the sum of the ones which arrived when only path B is open and those who arrived when only path C was open. In fact, if we set up this experiment carefully, we can arrange that if only path B is open, a non-zero number of atoms arrive at E, And if only path C is open, a non-zero number arrive. But if both paths are open, no atoms arrive at E. That's the phenomenon which, as some of you may know, is called total destructive interference. So it looks as if it cannot be the case that each individual atom selects either B or C. What you do say about this, that's a sort of negative statement. We can say it is not true that each individual atom selects either path B or path C. What you say positively is perhaps a matter of taste. You can say that each atom goes through both paths, or each atom goes through neither path, or the question doesn't really make sense. But the one thing you can't say is that each individual atom selects one path or the other. Okay, let's go on. Next slide, please. Now, that's the experimental situation. And so far, we haven't made any theory for it. But in fact, quantum mechanics does give a rather self-consistent account of what's happening. In quantum mechanics, each possible process is represented by something which is called a probability amplitude. And a probability amplitude is not the same, really, as a probability. In fact, it's something which can be either positive or negative. Actually, as many of you will know, it's a little more complicated than that in real life, but this will do it for our purposes. And then quantum mechanics says that the total amplitude to go from A to E is the sum of the amplitudes for the possible poles. That is, A goes to B goes to E, and or A goes to C goes to E. Now, that's the total amplitude. What about the actual probability to go from A to E? Well, that is simply the square of the total amplitude. Next slide, please. So let's just work that out, because it's a rather simple bit of algebra. So if path C is shut off, then the total amplitude is simply the amplitude to go through B, because that's the only possibility. And therefore, the probability under those circumstances, which remember we've defined as P sub B, is simply the square of A sub B. Similarly, if path B is shut off, the only possibility is to go through C. So the total amplitude is now A sub C. Again, the probability, which under these circumstances, we remember we call P sub C, that is A sub C squared. Now, what happens if both paths are open? In that case, the total amplitude is the sum, the algebraic sum, of the amplitude to go through B and the amplitude to go through C. And therefore, the total probability, which remember is what we call P sub B or C, that's given by the total amplitude squared. And you just do a trivial little bit of algebra, and you see that the way it comes out is that P sub B or C is P sub B plus P sub C, which is, remember, would have been the common sense result if you'd left it at that. But then you get this last term twice A sub B times A sub C. And this is called the interference term, and this is where all the problems stop. And let me emphasize that in order to get anything other than the common sense result, then the amplitudes A sub B and A sub C must simultaneously exist for each atom going through the device. Okay, there's just one more slightly technical thing I have to do before we can really get going. So let's just go to the next slide. This is the most complicated slide I'm going to have. Just recapping from the last slide, P sub B or C, probability of arrival at E when both paths are open, is the common sense result plus this interference term 2 A sub B times A sub C. Now let's suppose that for some reason A sub C is either plus A sub B or minus A sub B, and that happens at random. We'll see later how that can happen, but let's just make that as an assumption. Then the average of P sub B or C over all the atoms that are going through the device, well, that's the average of P sub B plus P sub C plus the average of twice A sub B, A sub C, but A sub B, the average of A sub B times A sub C is the average of plus A sub B squared and minus A sub B squared, and therefore it's just 0. So in other words, under those conditions, that nasty interference term goes away. And you simply get the common sense result, P sub B or C is simply the algebraic sum of P sub B plus P sub C. And that is exactly the result which you would get if you assumed that each system chose either path B or path C. So it looks as if, from this analysis, assuming that we believe quantum mechanics, what that seems to suggest is that when A sub B and A sub C simultaneously exist and and they don't have random signs, as I assumed above, then neither path B nor path C is selected. Well, this is a state of affairs which was realized very, very early on in the history of quantum mechanics. And initially, lots of people, both physicists and philosophers, were very puzzled by it. But eventually, the puzzlement of most of these people was removed, and the person who did most to remove it was the very famous physicist Niels Bohr. Next slide, please. Yeah, Niels Bohr is on the right there. And what Niels Bohr basically said, and he said this many times and in many places, was, look, you really should not expect things which occur at the scale of electrons and atoms to behave like things, the furniture of the everyday world that we inhabit. You shouldn't even think of an electron or an atom as a thing which could have any properties in its own right. It's really only a sort of link between an experimental preparation apparatus and an experimental detection apparatus. And therefore, it's not at all odd that when you don't look at the way in which an atom, say, is behaving in a given experimental setup, it might behave totally differently from if you were looking at it. And he said a great deal more along these lines, but that was his basic point. Well, as I say, Niels Bohr did convince an awful lot of his contemporaries. There was really no problem in the interpretation of quantum mechanics. However, there were always sort of counter-suggestible people around, and in this case, one very counter-suggestible person was the person on the left in this photo, and that's Owen Schrodinger. He was again one of the founding fathers of quantum mechanics, and he didn't really buy Niels Bohr's assurances. And to show why he didn't buy them, he constructed a famous thought experiment, which is in the next slide. So next slide, please. Right. So here we have a set of atoms which start from a given state A, and from there can go, well, as we would normally say, either down path B or down path C. And let's just think for a moment about the first atom which comes out of the apparatus. If that atom goes down path B, then it just goes away harmlessly and nothing happens. If it goes down path C, something more interesting happens. It triggers some kind of electronic counter, and as a result of that, the counter activates what Schrodinger calls a hellish device, and the device consists of a vial of cyanide inside a closed box whose other occupant is a cat, and a hammer which is activated by the electronics and can smash the bottle of cyanide. And I do note that this diagram is historically accurate. There is an unfortunate misconception in some places that Schrodinger's cat is either shot or electrocuted, but no, if you go back to the original paper, she is actually poisoned by the vial of cyanide. So this is accurate. Anyway, what's the point of what Schrodinger called this hellish device? Well, in quantum mechanics, if an initial state 1 evolves into a final state 1 prime, and an initial state 2 evolves into a final state 2 prime, then the quantum superposition of states 1 and 2 evolves into a quantum superposition of 1 prime, 2 prime. And that's a very, very basic feature of quantum mechanics. It's the so-called Unitarity Principle. If you want to question it, you can, but if you question it, you're no longer really doing quantum mechanics, you're formulating an alternative theory. So if we stick to quantum mechanics, that's the case. Now, you see, in this case, I should have mentioned, incidentally, when talking about the atom going through the original two-slit device, that the technical term for a state of affairs in which the atom goes through both paths, or whatever, it seems to go through both paths simultaneously, the word for that is a superposition. So indeed, atoms can occupy superpositions. And in fact, the atom which originates at A could perfectly well be in a quantum superposition of a state of going down path B and a state of going down path C. But path B leads to a final state in which the cat was alive, and path C leads to a final state in which she is dead. And therefore, by the basic principles of quantum mechanics, the superposition of B and C must lead to the superposition of states of the world in which the cat is alive and a state in which she's dead. In other words, you have a non-zero quantum mechanical amplitude for the cat to be alive and a similar non-zero amplitude for her to be dead. And it's not entirely clear whether that's more uncomfortable for the cat or for the theoretical physicist who has to contemplate it. Well, luckily, the animal protection societies, of course, have prevented us doing this experiment in any statistically significant way, but very few of us indeed doubt that if we were to take the lid off the box and look at a particular cat in this experimental situation, she would either be definitely alive or definitely be dead. In fact, we really wouldn't know how to recognize this state, this peculiar state that quantum mechanics seems to be describing. So that, in a nutshell, is the Schrodinger's cat paradox, and it has exercised both physicists and philosophers for something like 75 years now. And there have been literally thousands of papers in the literature which have claimed to resolve the apparent paradox. So next slide, please. So let's just look at a few of these alleged resolutions of the paradox. And I'll actually take these out of order. Let me start with resolution 2, which is what I call the extreme statistical interpretation of quantum mechanics. And what this interpretation says is, look, you are really taking all this stuff far too seriously. All that the formalism of quantum mechanics ever was and was ever meant to be is a recipe. It's simply a string of symbols that you write down on a piece of paper, which will enable you to start from some experimental preparation situation and to predict the probability of getting some final result. And beyond that, there is absolutely no reality to it, simply a recipe. Well, and so in particular, in the Schrodinger's cat situation, that peculiar final state of the cat, where the amplitude for being alive was non-zero and the amplitude for being dead was simultaneously non-zero, all that actually means is that if you were to take the lid off the box, then you would have some non-zero probability to find that cat alive and some non-zero probability to find her dead. End of story. Nothing more to it. This is at least a logically consistent interpretation, but I think it's in some sense a very pessimistic one, particularly for those of us like me who've spent many decades of our lives trying to understand and apply quantum mechanics, because at the end of the day, what it's saying is that, look, there's no reality behind these recipes that you're writing at all. You're not really learning about the structure of the real world. All you're doing is to predict probabilities. And that, I think, is a bit depressing. Well, maybe that's just a psychological factor. But anyway, a lot of people don't like that particular interpretation. So let's go now to 3, which is the other extreme, the so-called many worlds interpretation of quantum mechanics. And what the many worlds interpretation says is precisely the opposite of what the extreme statistical interpretation said. Remember, the extreme statistical interpretation said, don't take the formalism of quantum mechanics seriously. The many worlds interpretation says, take the formalism of quantum mechanics deadly seriously. When you have this, when you write down this funny final state of the cat, then that's what the world is like. The world really is in a quantum superposition, a state where the cat is alive, and the state in which she's dead. Then you say, wait a moment, I've just opened the box, and this particular cat looks like she's sitting up and mewing happily. What's happened to the part of the quantum description, the amplitude for her being dead? And then the advocates of the many worlds interpretation look you in the eye and say, well, what you have to realize is that there is a parallel world which is equally real to the world you think you're inhabiting, in which not only is this particular cat dead, but you're actually seeing her to be dead. And then they give you all sorts of formal theorems as to why there can never be any, as it were, interference between these different possible worlds. Well, I wish I could say something intelligent about the many worlds interpretation, but I fear I can't. And the reason I can't is that I quite literally do not understand it. And I mean that quite literally. When the advocates of this interpretation claim that these parallel worlds, which we are not conscious of and could never be conscious of by construction, and they say those worlds are, quote, equally real to the ones which we think we're inhabiting, those words sound like English. What do they mean? I cannot give any meaning to the statement that these worlds are, quote, equally real, unquote. I should say I'm not necessarily in a majority in that opinion. A lot of my colleagues, including a lot of people whom I respect, do somehow manage to believe the many worlds interpretation, but I can't. Well, as I say, it's not that I can't believe it, it's just that I do not understand it. So finally, let's briefly at least discuss the what is a really rather popular resolution of the Schrodinger's cat paradox, which is what I call the Orthodox Resolution, because it is the kind of resolution that I believe that many practicing physicists come to pretty much spontaneously once they start to think about it seriously. You recall that in general, in the two-path situation that I showed you, the probability of arrival when both paths are open is the common sense result plus the interference term. However, we also saw that if A sub C was equal to A plus or minus A sub B in a random way, then the interference term averages to 0, and you simply get the common sense result. Now, generally speaking, it's agreed that the effect of the outside world is, generally speaking, is to randomize the sign. This is the phenomenon which some of you may know as under the name of decoherence. And that gets more effective as the system gets larger. And so it's generally agreed that the interference term will, generally speaking, vanish for everyday objects like cats. So far, so good. But then it is claimed that, well, once the interference term has vanished, you might as well say that each system chooses either path B or path C. So this allegedly dissolves the paradox. I think that resolution involves a very severe logical lacuna. At the microscopic level, we could not apparently say that each atom chose either path B or path C. Why not? Because of the experimentally observed phenomenon of interference. By the time we get up from the microscopic to the macroscopic level, as in Schrodinger's thought experiment, we all agree that the interference terms have gone away. However, nothing has changed in the formalism of quantum mechanics itself. So if we cannot interpret the formalism of quantum mechanics at a microscopic level, the level of the atom, as saying that each atom goes through either path B or path C, then we cannot either interpret the formalism at the level of cats as saying that each cat is either alive or dead. So personally, I do not believe that the so-called decoherence or orthodox resolution is sustainable. Okay, well, let's just go back for a moment. Why did we get into this situation in the first place? We got into this situation because we implicitly assumed that because quantum mechanics describes very well, as we all agree, the behavior of electrons and atoms, and macroscopic everyday level material, everyday level things are made out of atoms and say atoms and electrons, then it must follow that quantum mechanics describes perfectly well the behavior of things in the everyday world, at least in principle. So we ask ourselves the question, well, how do we know that's true? The next slide, please. So let's make the opposite assumption. Let's assume that quantum mechanics breaks down at some point en route from the atom to the cat. And there's been a small subcommunity of physicists over the last 30 years probably, who have tried to explore this possibility and have produced various scenarios in which, in one way or another, quantum mechanics does break down as we go from the atom to the cat. Of these scenarios, probably the best known is the so-called Grwp theory. In that theory, there is a universal and a non-quantum mechanical noise background. It's very important that this noise background not be itself described by quantum mechanics. And that noise background induces a continuous and stochastic evolution to one or other of the two states of a superposition. The trigger is, at least in the original Grwp theory, is a large separation of the center of mass of a large number of particles in the two states. And the rate of evolution is proportional to that number, which are being, as it were, separated. So, so in fact, the effect of that is that we can have a photon, say, coming from the most distant quasar in the galaxy, which we currently see, and that photon is just one particle. So we can perfectly well maintain it in a superposition of states which, say, are at the different ends of a Michelson interferometer, and things will still work. In other words, we'll still get the standard quantum mechanical predictions. However, if you think about something like Schrodinger's cat, then the two states in which she's alive and in which she's dead correspond to a very large, well, certainly of the order of a foot separation of the center of mass of all the particles in her, something like 10 to the 30th. And therefore, that, according to the Grwp theory, that will very rapidly evolve into one of the two states. And that is not, as I say, this is quite different from the decoherence solution. This evolution is a real physical process, not just a mathematical nicety, as it were. Well, there are, as I say, that the Grwp theory is the best developed of these theories, but there are others. For example, Roger Penrose has a theory based on the special effects of gravity. I won't stick my flag on any particular one of these theories, but I will consider a general class of theories about the world, which I call macro-realism, which crudely speaking simply means that a macroscopic object which has available to it two macroscopically distinct states will at all times be in one or the other of those states. If you're a philosopher, you can perhaps question me at this point, what do I mean by be? But let's put that aside and for the moment and assume that we have some intuitive notion of what that means. So now let's raise the question: can we actually test the hypothesis that, well, can we actually do an experiment to distinguish between these two possible hypotheses? Remember, hypothesis number one, or A in my notation, is that quantum mechanics continues to apply not just to atoms and electrons, but to counters and cats and perhaps even in the last resort to ourselves. Conjecture number B is macro-realism, that something else takes over from quantum mechanics as we go from the atom to the cat. Okay, next slide, please. So, which is right? How do we tell? Well, now there's a problem, you see. If in fact it really is true that all everyday scale bodies have the property that the interference term is always randomized, in other words, if they always show sufficient decoherence, then we're always going to get the common sense result. In other words, all the experimental results will be just as if one path or the other were followed, just as if macro-realism were right. In other words, we can't tell. So what we have to do is to find some everyday scale object where decoherence is not effective. And the question is, does any such exist? And when I and a few other people started pushing this program, which was way back around 1980, we got a lot of flack from the professional quantum measurement people. They said, this is absolute rubbish. Everyone knows by the time you get to the level of everyday objects, by any reasonable definition of everyday scale, then decoherence is certainly going to kill you stone dead. Well, not true, actually. What's essential is a number of things. First of all, the difference of the two states has to be at the everyday level. Otherwise, there's no point in doing the experiment. But nevertheless, the relevant energies involved must be at the atomic level. And at first sight, those two conditions would look as if they might be incompatible, but not true. You must have an extreme degree of isolation from the outside world, because remember, it was mostly the obstruction, as it were. I don't want to use the word interference, but the obstruction by the outside world, which or the messing up by the outside world, which led to decoherence. So you don't want to have contact with the outside world. And finally, it turns out that even intrinsic dissipation, that is intrinsic to the system itself, will lead to decoherence. So you want to avoid that too. Suppose you imagine that you found such an object, and as we'll see, such objects do exist. How are you going to tell what quantum mechanics predicts here? Well, unfortunately, the quantum mechanical calculations for this kind of object are very hard. You don't want to base yourself on an a priori microscopic description, because if you do, and you do the experiment and find a result which you had not predicted, then your opponent can always come back and say, well, you just started off from the wrong microscopic description. So what you actually can do, and this has been a bit serendipitous in this area, is that you can start, it turns out, not obvious at all, but it turns out you can start off from the experimental behavior of your system in the classical limit and measure various parameters in that limit. And then it turns out, again, this is the surprising and very serendipitous thing, it turns out that these parameters are all you need in order to predict the quantum mechanical behavior. And so this experimental program then is becoming, as it were, somewhat reasonable. Next slide, please. Yeah, okay, let's see how we're doing for time. Yeah, okay, I'd better perhaps try to speed up a little. This is just an electron micrograph provided courtesy of my experimental colleague, Delvin Harlingen at the University of Illinois, which is a typical system on which we might try to do this kind of experiment. It's something which used to be, in the old days, around 1980, it used to be called a radio frequency squid. Nowadays, it has the more glamorous name of a flux qubit. It's a bit of electronics involving the Josephson effect. This is just to show the scale. You can see the 0.5 millimeters at the top, but the operative bit of it is just this little bit that you see in the bottom diagram there. Now, let's see, next slide, please. Yeah. Okay, I think at this point, perhaps I should skip the details of the theory which apply to it, but let me just try to very quickly summarize. This is the object in question is superconducting, and superconductors are believed to be characterized by the existence of pairs of electrons, which we call Cooper pairs. And the important thing about Cooper pairs is that they behave rather like helium-4 atoms. They behave like so-called bosons, and that in turn means that they must all behave in exactly the same way at the same time. So I'll skip the details here, but let's just go on to the next slide, please. Next slide, please. Yeah. Okay. So yeah, so the Cooper pairs, once they form, must automatically undergo a phenomenon which I won't go into in detail, which is called Bose condensation, but what it means is they must all do exactly the same thing at the same time, and that's true also in a non-equilibrium situation. So we're going to make a particular application of this principle. Next slide, please. Yeah. So let's imagine a simple superconducting ring in an external magnetic flux. There are, and I'm going to apply an external magnetic flux through the ring. Now, if that flux is 0, then it turns out that the ground state is unique and all the pairs are simply at rest. But if the flux is half a so-called flux quantum, that's h over 2e, which we can ensure, then the ground state is doubly degenerate. In other words, you have two states with exactly equal energy. In one of them, all the pairs of electrons are rotating clockwise, and the other one, they're all rotating anticlockwise. Now, you might ask, well, hold on, why can't half the electrons rotate clockwise and half of them anticlockwise? Well, that's the point of Bose condensation. If they try to do that, then it turns out that state has a grossly increased energy. It is not anything like the ground state. So if you take them to sufficiently low temperatures, so that they basically want to go into the ground state, either all the pairs must be circulating clockwise or all anticlockwise. So far, so good. Now let's do something a bit more complicated. Next slide, please. Yeah. What we can do is to put into that ring, into this bulk superconducting ring, which we've constructed with flux through it, we can put in a so-called Josephson junction. And if you don't know what a Josephson junction is, just think of it as a sort of gate, which will allow these electron pairs through, but with increased difficulty. And it turns out, again, this is not at all obvious, I'm just telling you, it turns out that under those conditions, the quantum mechanical ground state is neither one in which they're all going clockwise, nor one in which they're all going anticlockwise, but a quantum superposition of the two. And let me stress very, very strongly that quantum superposition is not a state in which half the electrons are going clockwise and half anticlockwise. It's a completely non-classical combination of a state in which they're all going clockwise with one in which they're all going anticlockwise. And so the question is, can we actually get evidence for that that state is realized? And it turns out, yes, we can. But the simplest way to do it, the original way, historically, was spectroscopic. If you plot out the energy levels of that system as a function of the external flux applied, then you find that if you make the assumption that it's always all clockwise or all anticlockwise, then the spectral lines, spectral frequency behaves in the way shown by the Peck dashed lines, grey lines in the diagram. If, on the other hand, you assume that the true state is that funny quantum superposition, psi, then you get the green lines. And crudely speaking, two experiments at SUNY and Delft in the year 2000 did that, and they found the green lines. And the more spectacular experiments, somewhat more recently, you can actually see the system oscillate coherently between one of those two states, that is, between all clockwise and all anticlockwise, just like an ammonia molecule, basically. So that's all very fine, and it looks like quantum mechanics does seem to be giving the correct description still. But next slide, please. Okay, I think we can skip this one. Next one, please. Yeah. Okay, what we've shown, and there've been, I should say, there've been a whole lot of similar experiments over the last 20 years, getting more and more sophisticated. But until recently, all that they had actually shown was that quantum mechanics works. Saying that quantum mechanics works is not the same as saying that an alternative scheme of things does not work. What we would really dearly like to do is not just to show that quantum mechanics is working, but to show that an alternative picture of the world, that is a macro-realistic picture in which at the everyday level, things were always doing one thing or the other. We'd like to show that that does not work, at least at the level of this squid or flux qubit. And it turns out that, at least in principle, we can do this. And this is something that my then postdoc Anupam Garg and I showed way back in 1985. For a squid or flux qubit, you can define the class of macro-realistic theories by the following postulates. First of all, macro-realism itself, the system is always either in state plus, or in state that is always clockwise, say, or state minus, or anti-clockwise. And that's true whether or not you're observing it. Secondly, in principle, you can determine, this is the difficult bit, you can determine whether it's plus or minus without any effect on its subsequent behavior. That technically that is called non-invasive measurability, and that's been a subject of some controversy in the literature. And finally, induction, crudely speaking, the arrow of time does what you think it normally does. And if you make those three postulates, then you can actually write down a certain quantity k, whose value can be directly inferred from an appropriate series of measurements, and you have various predictions of k. First of all, any macro-realistic theory will always predict that k is less than or equal to 2, and I think that's a matter of general agreement. Secondly, quantum mechanics in the ideal situation for a totally isolated system, which is perfect in its working, that predicts that k is 2.8, which, needless to say, is not less than or equal to 2. Finally, if we take into account all the real-life complications, but nevertheless do the best quantum mechanical calculation that we know how to do, then I think most people will agree that the prediction is that k is greater than 2, but it's less than 2.8, but it's still greater than 2. So, in other words, the experiment does make sense. And to the extent the analysis is reliable for part C, you can actually do a meaningful experiment to force nature to choose between quantum mechanics and macro-realism, at least at the level of flux qubits. Next slide, please. So, when we started thinking about this, we realized, and people have pointed out ever since, that there are several possible outcomes of that experiment. The most likely experiment, the most likely outcome the first time the experiment is done is that it doesn't work. In other words, there's too much noise so that the quantum mechanical prediction for k is actually less than 2. As a matter of fact, that turns out to be too pessimistic, as we've found over the last 20 years or so. Second possibility, k is greater than 2, at which point, at least prima facie, macro-realism is refuted. And thirdly, third possibility, k is less than 2, again, prima facie, quantum mechanics is refuted at the everyday level. If the experiment were to come out, according to C, that would not by any means be the end of the story. And most people would say it's a bad experiment and you have to go back and redo it and so forth. But anyway, turns out we don't have to worry too much about that, because this was the situation up to October 2016. But at that point, we did do, not that exact experiment, at least one closely related to it. And let's see the last slide. Yeah. So in November 2016, that experiment was done and published. A group at NTT in Japan did the experiment. I'm a co-author on the paper because I did some theoretical analysis for it. Anyway, important result is B. That is, k is greater than 2. The quantum mechanical result knocks out macro-realism by more than 80 standard deviations. So I think we can at least conclude that macro-realism does fail, at least up to the level of superconducting devices. How macroscopic is that? That's, again, as always, a debated matter. But I have an argument, and if anyone's interested, I can tell them the reference to that, that this superconducting device is at least as macroscopic as the smallest dust particle that you can actually see with the human eye. So I would say that we really are getting into, in some sense, the macroscopic or everyday domain. So quantum mechanics works so far, at least in these special systems. Where to go from here? We could go to bigger, to larger systems. That wouldn't be particularly interesting, I think. What I think would be much more interesting is to go to try to get closer and closer to our own direct subjective experience. And one observation in that context is that although people argue, there's a big argument in the psychophysics community about what is the minimum number of photons which is necessary to trigger the rhodopsin, which is the basis of human vision. But everyone agrees, I think, that half a dozen will do it. So it ought to be quite rather simple to devise, at least in principle, an experiment in which you create a quantum superposition of no photons and say 6 photons. And then by the Schrodinger's cat kind of argument, that ought to result in a quantum superposition of the rhodopsin in my eye, which is a quantum superposition of being triggered and not triggered. Unfortunately, as at the moment you say this to any practicing biologist or biochemist, they'll just tell you, well, yeah, but biological systems by their natures are warm and wet, which is their language for saying they're absolutely full of decoherence, basically. So probably that experiment won't work in a simple form. But I do believe that that's the way to go, to try to devise more and more sophisticated experiments which take, if you like, the Schrodinger's paradox, cat paradox, closer and closer to our own subjective experience as human beings. And, well, we just don't know. And maybe it'll turn out that quantum mechanics just does keep working forever. In which case, well, we have to, I think, accept the statistical interpretation and just grin and bear it. I still have a fair degree of confidence it won't keep working forever. How it's going to break down, I don't know. Where it's going to break down, at what point it's going to break down, I don't know. That it's going to break down, I'm fairly confident. Thank you.
Thank you very much, Tony, for such a nice talk. So let's take some questions. Nancy, just go ahead and unmute yourself.
Hi. Very, very nice colloquium. Thank you. Was very clear. One question that I had is, what is the problem with the statistical interpretation? Why? Because as humans, I understand that we have difficulty thinking in terms of statistics. It seems to me that the way that we are wired is not the best way to think in terms of statistical concepts. But that doesn't mean that nature doesn't work with the statistics.
Yes,
so
indeed.
No, go ahead. Yeah.
Yes, indeed. And I think the point of view which you just expressed is one which perhaps an increasing number of physicists who spend a lot of time thinking about these problems have come to. For example, I think this is basically the point of view of David Mermin, who's a rather well-known authority in this area, Chris Fuchs and others. What I can really say is I find it very uncongenial. Because basically, you see, what it means is that at least in certain circumstances, not only is there really no answer to the question, what was the state of this particular cat before I took the lid off the box and looked at her? I mean, in some sense, there's really no meaning even to the question. Well, maybe we have to live with that. It is possible. after all, I think it's similar, if I can just digress very slightly, it is related. We do find a rather similar situation with regard to counterfactual statements. You know, in everyday life, we make counterfactual statements the whole time. You know, had I got up 5 minutes earlier this morning, I would have caught the 8 o'clock bus, something like that. No one ever doubts that these are meaningful, but if you start really thinking about it, you start to realize that maybe there is no definite meaning to this. And certainly there are some experiments, again in the foundations of quantum mechanics. These are so-called, you probably know, the so-called EPR Bell experiments, which do seem to indicate, or at least one possible interpretation is, that indeed counterfactual statements really have no meaning, which is oddly enough something which the philosophers might not be that unhappy about. This has been a big issue in philosophy for hundreds of years. So I suppose they would be more prepared than I am to go with that. But yes, I mean, it could just be that that's the way the world is, that we've been used to for thousands of years. We and our ancestors have been used to a world in which quantum mechanics really doesn't make any difference. Now we're finding that it really is coming in to make a difference, and we're not used to it, and maybe we just have to get used to it.
Okay.
More questions? So I have a question myself.
Yeah.
So you mentioned this community about these many words interpretation.
Yeah.
How big is that community? And
yeah, a good question, actually. And one actually which has non-trivial social consequences, believe it or not. As I say, personally, I just do not understand it, and so I can't say much more about it. However, if I do a bit of sociology, as it were, what is the proportion of physicists who believe it? Well, one physicist who certainly believes it very seriously indeed is David Deutsch. I don't know if you know his name, but he is actually what you might call a non-traditional physicist, in that he's not, I think, regularly employed by any institution. He's privately financed and so forth. But he did a very important piece of work way back in 1984, which essentially laid the groundwork for the more recent work of Peter Shaw on quantum computing. And David Deutsch really, in some sense, did kick off the idea of quantum computing, along maybe with Feynman and one or two other people. But anyway, David Deutsch repeatedly claims, and he's published, said this in print several times, I think, that the fact that a quantum computer works at all implies that the many worlds interpretation must be right. And I think that's complete nonsense. All you need for a quantum computer to work, I mean, assuming it does, and I think that's a bit up in the air right now, but all you need is that the formulas of quantum mechanics does predict the correct results, provided that you make the so-called measurement postulate at a sufficiently late stage in the operation. And that's all we have any evidence for right now. So no, to my mind, in some sense, no experiment could ever prove the many worlds interpretation, quite simply because it's incoherent. But so that's my opinion. David Deutsch thinks otherwise. And to my surprise, not only a fair number of fairly sophisticated physicists do seem to agree, but also, much more surprising, some professional philosophers. I was really rather shocked to find that Simon Saunders, who's a rather well-known philosopher of physics, among other things, in Oxford, did seem to take the many worlds interpretation rather seriously. But what is actually rather frightening, I think, is that some years ago, let me just tell this little story. Some years ago, to make a point about the many worlds interpretation, or rather its incoherence, I devised a thought experiment. What happens is it's basically a sort of Schrodinger's cat experiment, but with 10 possible channels, 10 possible outcomes. So you are presented with an experiment which you can do, which has 10 possible outcomes. And in 9 of those, nothing at all unpleasant happens to you, and you can claim a large reward of whatever kind you need. In the 10th possible outcome, you are painlessly but definitively disposed of. You die. Okay? So you won't feel anything, but you die. Are you prepared to undergo that thought experiment? Okay. So what I'm going to do is to set up this 10-channel Schrodinger's cat, if you like, and ask you, are you prepared to undergo that experiment? If you really believe the many worlds interpretation, you should be prepared to undergo it, because in 9 of those possible outcomes, which remember are all equally real, you will be very happy. It's only in the 10th one you'll be unhappy. But I propose this as a joke, basically. But apparently there is a sub-community of people who take that seriously and have gone in at one time or another, this sort of Russian roulette. And I think there have been actually quite literally 1 or 2 fatalities because of this. That really scares me. I really rather wish I hadn't proposed anything. Well, I'm sure someone else would. So that's the best answer I can give you.
Thank you. Jorge, you have a question?
Yes. Thank you very much for your nice talk. I would like to ask you about your opinion on the proposal of Penrose that the gravitons have to do a lot in the direction of collapse of the wave function, and if there is some kind of experiment that can be proposed that they could test that idea.
Well, yes. I mean, obviously, in order to make that kind of proposal testable, you have to spell it out. Sometimes what degree of interaction with gravitons is going to collapse your wave packet for you. Now, Penrose did, in fact, specify a possible version some years ago, and Dirk Baumeister, I forget where he's working right now, but he's, I think, Santa Barbara, maybe, UCSB, I think. He did set up an experiment to try to test that. As far as I know, that experiment has been running for several years and has not actually given definitive results one way or the other right now. But if it fails, I mean, if it just shows the standard quantum mechanical results, then of course Penrose can legitimately go back and say, well, okay, we need to set the, as it were, the critical parameters at which you're going to see a reasonable effect to be slightly smaller. And so you need a more precise experiment. And you can think of doing the same kind of thing with these flux qubits that I was mentioning. You know, just make them more, make them larger, make them more complicated, and so on and so forth. But as I say, for me, that really isn't the most interesting direction to go. I think I would rather try to push things closer to our own subjective consciousness if we can find a way of doing it.
Thank you.
Thank you. So there is I think this will be the last question. It was typed in the Q&A section. So it says, what's your opinion about Mobian mechanics in the context of your talk? This seems to be okay with the failure of macro realism, and it does not affected by the measurements problem.
I'm sorry, could you just repeat that? I didn't quite get what the question was.
What is your opinion about Bohmian mechanics.
Bohmian. Okay. Yeah. Well, okay. My crudely, I'll give you a rather quick reply. Crudely speaking, my view of Bohmian mechanics is that it's really, how to put it, intellectual window dressing. That is your, but at least as, okay, maybe I should just go back, say something a bit more. Historically, what Bohm was originally trying to do was to formulate an alternative to quantum mechanics. That is, he was trying to formulate a theory somewhat, in a way, somewhat analogous to the GRWP theory that I mentioned. He's trying to formulate a theory which, under, as it were, existing normal conditions, would give results identical to those of quantum mechanics, but under more extreme conditions would give different results. So it is not an so originally he did not have an interpretation of quantum mechanics, he had an alternative theory. Now there was a particular parameter in that theory which he didn't really know, and he basically made a guess at that. It was a parameter with the I guess the dimensions of frequency, and he just chose it to be KT over H bar effectively. But that was sort of rather crude guess, and he admitted that. Now, most people didn't take that too seriously, but in 1967, I think, Papaliolios actually decided to do a test. And he did a test which was meaningful if that parameter which Bohm devised did have the value he said he guessed for it. And Papaliolios' experiment just came out according to standard quantum mechanics. And at that point, I don't know what Bohm himself, I mean, because Bohm was still very much alive at that point, I'm not quite clear what his reaction was, but most people who called themselves Bohmians at that point sort of decided to pretty up to fix up the Bohmian approach so that it would simply give results exactly equivalent to those of quantum mechanics. Now, if that's the case, then I claim it merely is verbal window dressing, effectively. All you're doing is to put new words on the predictions of quantum mechanics, and I personally don't see any great point in doing that. As far as I know, no one has really tried to resurrect the original idea. In other words, that you actually do try to create a genuine alternative to quantum mechanics. I don't see why it shouldn't be done, but no one seems to have found the motivation to do it so far, at least.
Thank you, Tony. I think that's it. There are no more questions. Well, thank you very much for your talk. Thank you very much, everyone, for coming. And I hope to see you in the next colloquium.
Good to see various people I recognize. Yeah. Okay.
Thank you.
So I'll talk out them. Yeah. Okay.
Bye-bye.
Bye.